So last time we had started talking about fractal dimension or fractional dimension that fractals can have. Topological dimension is just our normal 1, 2, 3 dimensions. And then Hausdorff dimension here was defined by this exponential relationship, which if you solve for the dimension, you get log of cap n over log of cap p over little p. And n didn't need to be an integer here. Your object had size p, usually taken to be size 1. Cap p constructed of smaller units of size little p, that was our magnification factor, and cap n is your number of smaller units that replace the object. So for the Cantor set here, we started out with something of size 1. So length here is equal to 1. And then we replace that by removing middle 2/3 with 2 pieces. So cap n is equal to 2. And then little p is equal to 1/3. So each of these pieces was 1/3. So this is length 1/3. So 1/3 the size of the original. So our Hausdorff dimension for the Cantor set here is the log of the number of pieces, n, here, which is 2, divide by the log of, and we're taking cap p to be 1, so this would be 1 over little p, so 1 over 1/3, and you got a double reciprocal in there. That is log 2 divided by log 3, and to 2 decimal places, that is 0.63. So this fractal dust, the dust from the Cantor set that's left after you remove the middle thirds infinitely many times. Remember we showed that had length 0. It has dimension 0.63 by this definition. So it's more than 0, it's more than a point, but it's less than 1, it's less than a line. So dimension of the Cantor set is between a point and a line. Let's look at another example here. So this is what's called the Sierpinski triangle. So that's stage 1. And stage 2, you remove the middle triangle here. So you divide it in half along the sides here. And then those 3 points determine an inverted equilateral triangle. And then you keep doing that. That's stage 2. And then for each one of these triangles, you remove a middle triangle inverted. That's stage 3. And you keep on going. So if you do this, you will have infinitely many points in the plane that are left. But actually, the area of what's left will be 0. So 0 in area, but still infinitely many ordered pairs. So if we take, so if this side length of stage 1 is 1 unit, then in the next stage, each one of these smaller triangles has base 1/2, and its height is also going to be 1/2. So the magnification factor, little p here, is going to be 1/2. Each big triangle gets replaced with 3 smaller ones. So cap n is equal to 3. And again, we're taking cap p to be equal to 1. So then our fractal dimension, or Hausdorff dimension here, is going to be the log of n, which is 3, over the log of 1 over 1/2. So log of 2. So log 3 divided by log 2. So log 3 divided by log 2 is 1.58. So that is somewhere between a line and a plane. Somewhere between 1-dimensional and 2-dimensional. Pretty cool.